Welcome, everyone. Happy Friday. My name is Daniel Rodriguez, and I am a professor of city and regional planning and associate director of the Institute for Transportation Studies. So welcome to our seminar series, Applications of Data Science and Artificial Intelligence to Equity, Race, and Inclusion in Mobility and Transportation. So I wanted to give a little bit of context of this about the seminar series and this topic, and how we came to it. We felt that the rapid growth of data science and AI applied to mobility really holds great promise for reducing costs, decreasing errors. But we also understand that there's significant harm potential as we train algorithms on data that often might be biased. We might be operationalizing, we might be amplifying, we might be legitimizing historical discrimination. And in some cases, discrimination that technology was intended to address in the first place, or at the very least, it was supposed to ignore. So these tools really raise fundamental questions in law, in the social sciences, in philosophy, and in public policy, questions that really have been impossible to ignore now. So our aim with this seminar series is to reflect on and raise awareness of applications and opportunities, potential misuses of these techniques in mobility and transportation, and specifically as it refers to race, equity, and diversity. We want to bring a unique and innovative perspective to existing discussions around this topic. And that really brings us to today. We're very excited to welcome Bill Howey. Bill is associate professor in the Information School at University of Washington, and also an adjunct associate professor in the Allen School of Computer Science and Engineering and the Department of Electrical Engineering, all at UW. His research interests are in data management, machine learning, and visualization, particularly as applied in the physical and the social sciences. Bill is founding associate director of the UW eScience Institute, where he has collaborated with colleagues at NYU and also at Berkeley. He's also a founder of UW's Data Science for Social Good program and of UW's Data Science Master's degree, serving as its inaugural program chair. And he also created a first MOOC on data science that attracted more than 200,000 students. Bill has a distinguished funding record, including support from the MacArthur Foundation, the NSF, Microsoft, and the Sloan Foundation, among others. His research has been featured in The Economist, in Nature News, among others. He has authored award-winning papers and conferences across data management, machine learning, and visualization. Bill has a PhD in computer science from Portland State University and a Bachelor's of Science degree in industrial and systems engineering from Georgia Tech. So today, Professor Howe aims to learn fair, reusable, integrated representations of heterogeneous city data to improve the performance of mobility prediction tasks while accounting for equity considerations. I want, before passing on the mic to Professor Howe, I want to acknowledge the co-sponsorship of this talk, the Center for Information Technology Research in the Interest of Society, the Citrus Center, as well as the Banatao Institute and the College of Engineering. I also want to acknowledge my colleague, Jane McFarlane, who is helping me co-organize this seminar series. So thanks to everyone for being here. We're looking forward to a wonderful presentation by Professor Howe. The questions, please, if you have questions as Professor Howe goes through his presentation, just use the Q&A button on the bottom of your Zoom screen and you can type it in. And towards the end, I will be reading those questions out loud for Professor Howe's consideration. So having said that, I will pass on the baton to you, Bill. The floor is yours. Welcome.
Thank you so much. I was thinking about topics and angles to talk about some of our work, and I decided to go with some things that are pretty fresh. So I'm going to try to give a bit of a background, given that there may be folks from different sort of interdisciplinary areas in the room that may have different, varying understanding of some of the basic techniques that we're trying to use, and also try to motivate some of the more state-of-the-art things that we're trying to push. So this is a bit of a cutting edge for us view of our world here. So yeah, so it's a bit of a mouthful. So we're talking about these learning fair integrations of urban mobility data, and I'll try to explain what I mean by that. I'll also mention that, you know, the connection with Berkeley, you know, you mentioned the eScience Institute. So the bids in eScience and then the CDS at NYU have this, you know, luxury of being kind of the old guard in the data science institutes around the country. And you know, where the age is, you know, 8 and 9 years is old time now. So I'm proud to come back and be able to talk about some of the work that we've been doing in this context. Okay. So my other affiliations besides the eScience Institute, just to flash them up here, we think about public interest technology locally, regionally, and nationally, and have kind of different affiliations with respect to those. And then there's a group that I lead that's really about more core methods. And so perhaps that's the most relevant affiliation for this talk. So this Urban Analytics group, where we talk about responsible urban data science. All right. So today what I want to do is give a little bit of background on deep learning and urban mobility, and some of the work that we've been paying attention to see where things are going, and then talk about this EquiTensors idea in sort of 3 parts. One is integrating open data from a lot of different sources. Perhaps the most important part is how to incorporate fairness and equity, which is really maybe the main theme here in this seminar series, and then briefly talk about a couple of experimental results, and then leave time for some questions and discussion at the end. So on the background, there, you know, as data becomes more available, you know, we used to talk about in the context of the eScience Institute with, you know, the sensing technology becomes more prevalent in really all fields. And I used to kind of give talks about how this is happening across all fields. But with the advent of data, the prediction problems become less of an esoteric thing and more of an everyday kind of thing. So we see this happening in all different areas, especially in mobility. And so, you know, there's papers on predicting citywide crowd flows with walking, traffic speed prediction, ride hailing demand, bike share, something that I'll talk a few more, give some more information about, because there was a bit of an interesting social and business experiment going on in Seattle over the last few years. Traffic accident prediction, and so on. Okay, so it's less of a review the data and ask questions about it, and more of trying to make predictions about the future, because the tools and data required to be able to do that are becoming commoditized and ubiquitous. All right. And so I'm going to intersperse a little bit of I added these slides a little bit at the last minute just to make sure that we were on the same page, so I didn't throw too much jargon at you. But just a bit of a background on my view of where deep learning is and was and will be. The key thing here is that, in contrast with ordinary machine learning methods, you know, you don't have this manual step of feature engineering. Okay, so if you have a picture of a car and you're trying to decide whether it is a car or not a car, the conventional way of doing this would be to say maybe, well, let's measure the length of the car, or the height, or the number of wheels. You know, design a bunch of features and then put that into the machine learning model, which would then adjust the weights accordingly and make a prediction about whether it's a car or not. But that's and that can work really well. But the observation has been that it kind of depends crucially on how good your human engineered features are. And so this approach of deep learning says, well, what if we could skip that step and just take in the raw images, or raw speech, or raw text, or raw data from whatever source you're getting it from, and automatically extract the weights, or automatically extract the features as well as the weights as part of the model. And so the trade-off here is that this works remarkably well, but it's extremely data hungry as well. It requires many examples of correct inputs and outputs to be able to figure these things out. Okay. And so if the manually designed features tend to be overspecified and kind of incomplete, they take a long time to design and validate, the success of your machine learning system really depends crucially on how well you've done that work. And here, learned features are easy to adapt and fast to learn. And it's extremely flexible and arguably close to universal framework. So as long as you have enough input-output examples, any function you might dream up is something you could potentially learn from with these methods, with perhaps appropriate asterisks around computational time and other kinds of things. But essentially, there's no obvious limit to the complexity of the functions you can learn. Okay, as long as given enough data. Okay, and so at some point in around 2010, these deep learning methods started outperforming conventional techniques in speech and vision, and then in NLP, and really in every other area as well. Again, as long as there's enough data around. Okay. And so just briefly, how these things are trained is you pass data forward through this multi-layer network, figure out how close you got to the right answer, and then back propagate those errors back to adjust the weights, and then keep going and going and going and going, and eventually the forward pass will tend to give a correct answer. Okay. And then after 10, 15 years of this, there's thousands of papers on all the details around this. But basically, this is the overall framing of how it works. Okay, so back to urban. Well, one way to frame a arguably broad class of urban prediction problems is, take a state of the world for some data set you want to predict at time 0, and that's kind of a 2D map looking down over the city. And take a time series of those maps and use all that history to try to predict the next time step. And so this could be, again, traffic flow or crowds or ride share, or maybe even things like crime, although that's not a good idea for other kinds of reasons. Actually, let me ask I think I understood that there's some students in the room too, so maybe I'll ask that real quick. Since the seminar is about equity, why is predicting crime a bad idea? It's maybe hard, but I want to see if people are willing to. I guess I can't see your responses, so I'll trust and see. If we go too long, I won't pester you too much, but I just want to see if we're able to fish out some engagement. I'm going to make the point in a little while that probably all of this is very dangerous, and I think Daniel said well that this is this entire enterprise is a bit of a risky venture in cities, and I'll try to say more about that in a few minutes. But crime in particular, I think, is a very questionable idea, even though people are doing it routinely.
Professor, you have 2 people who raised their hands. Do you
want
to hear
go
from
ahead.
Bing Yu, Xiao?
Oh yeah. Is it because if we predict crime, the police will be there and that will change it?
That's a good guess, but I guess even before we get there, if we predict crime, I claim we're not predicting crime when we think we are. So what is the data we have available to us when we try to predict crime? Do we actually have crime data, or do we have something else?
There's another one, Professor Kanefani. Oh, he dropped off.
So I was trained by my advisors to wait longer for questions, but given that I'm not in control of the time clock here, maybe I won't pester you too much. But one example you find here a problem you see in general throughout this space of trying to use fancy machine learning methods to make predictions that involve people. Things can go wrong. And so in crime, my major complaint, I have several, but my major complaint is we don't actually have crime data, right? We don't know where crimes are occurring. We know where arrests are occurring, right? And so if you want to train a model to predict where arrests are occurring, you can do that, but the model is going to do the obvious thing. It's going to tell you where, you're more modeling police behavior and police practices than you are anything about crime. And so the model is going to happily tell you that you should head right back into the poor neighborhoods and make more arrests, and they will. And then it'll look like, oh, the system worked. We had this fancy machine learning model that told us where the crimes were occurring. It worked. We made arrests, but all of it is a feedback loop based on police behavior. And so we don't have the right information to try to predict that. There's also other reasons why it's a bad idea, because you're somehow modeling, you're imagining that criminal behavior is some predictable thing based on past history, which is not quite clear. But that's a more subtle argument. In transportation mobility, I think the argument is a little more solid of why you might want to do this. Okay, past traffic history does probably predict future traffic patterns. Okay, so we'll say more about that in a little while. So I'm hoping you'll buy that this framing is not the only way to do urban prediction, or not the only kind of problem you might want to engage on in urban prediction, but this is one exemplary framing of the problem, right? Given a bunch of history, try to predict the next time step. Okay. And so the one conventional approach for this that doesn't involve deep learning is, well, imagine every little grid cell in this 2D map, in this stack of 2D maps, this little movie that's playing out of traffic or anything else you're trying to model. Take each little grid cell separately and use some time series prediction modeling that we can pull off the shelf or from some library. Okay, and so that works okay, but what it loses is the correlations in space, right? It kind of assumes that every single grid cell is completely independent of all its neighboring cells, which is of course not the case. Okay, so that there are approaches that do that, and they do okay, but they're kind of known to not be ideal. And so a fancier way to do this is to try to bring in some kind of how to adapt some of this deep learning stuff into this area. And so this was just a picture of a multi-layer network for no other reason, just to get that image in your head. But a couple of common practices or extensions to core deep learning that you should be aware of that are out there in the world and extremely popular, and many variants have been proposed. One is take a whole stack of these networks and put them in a sequence, and this allows you to take as input or produce as output sequential things as opposed to things of fixed size. So a sentence, right? Some sentences are short and only have a few words. Other sentences are long and have 25 words. Each word, each one of these elements in this sequence would be for predicting one word. And this is a this is a very, very severe oversimplification of what's going on here, but roughly you can think about that. So the key thing you're trying to solve though is to be able to produce things of varying length. And so a time series is a varying length. So you want to use some of the sequential tricks to do that. Another common practice that has been wildly successful, that was actually proposed in the 80s, but the computational power was so bad back then that it wasn't clear it really worked that well. And then once GPUs came around some number of years ago, it started to take over the world, is this notion of convolutional networks. And so the idea of a convolutional network is to slide a little filter over your input, in this case, usually in an image, but it can be anything, and compute some aggregate. And that's one layer in your network is to do this convolutional stuff. And so you come in with a raw input and you come out with this kind of smeared out convolved version of it. And the advantage of this is that you get some of the spatial coherence incorporated into your features automatically by sliding this window over the input. Okay, I thought I had one more slide about that, but there's a okay, fine. So that's not going to be terribly intuitive from this picture, but it allows you to do things like if I have a handwritten number 7 and I'm trying to recognize which number it is, if I smear it out a little bit in various ways, I get more examples of number 7s to learn from. And so that's another reason why this works so well, is instead of having just the, for every one example of a hand-drawn number I have, now I have 25 examples of it that are smeared out in different ways, depending on which filter I used over this. So it gives me more data from which to learn, which is important because these things are data hungry. Okay, so if we have sequential stuff and we have convolutional stuff, we can combine these, going back to urban, we can combine these in different ways. So we could say, well, let's use these sequential models, and one of which is called Lstms, long short-term memory models, as opposed to conventional time series prediction. And that works okay. So you encode the time series on one side and then you decode it on the other. So you're gonna learn some representation and then try to reproduce the original input from it, right? So I'm trying to not use jargon, but learn the latent representation and then reproduce the output, and the model gets trained by how well you're able to reproduce the original input. Okay, and that works okay. And then there's some tricks, for example, in this paper that I'm citing, to bring in the spatial information as well, but primarily it's an LSTM based model. You can do what perhaps is the obvious thing. The way I framed it is to say, well, look, convolutions are pretty good for images, and LSTM is good for sequential stuff. Let's put them together and use convolutional for the space and LSTMs for the time, and design our network that way. And that's been proposed as well, and been applied to accident prediction. And so what I'm trying to get across is all, the different variations of these network designs have been proposed in various pockets. So there's a kind of an active space of kind of trying to figure out what is the right way to do this. All right. Another trick you can do, which is what turns out to be, I won't say the best, but better than others as of nowish. There's some fancier techniques that are starting to come out, but roughly, if you take away what is the right way to do this, you can think about just using convolutions, ignore that sequential stuff, but do your convolutions in 3D as opposed to just 2D. So instead of just being in space, you can slide a little 3D filter over it and make some progress that way. Okay, and so this is the technique that we're gonna use as a basis. And the example I'm going to refer to every once in a while is bike share demand prediction. And this is not the perhaps the most societally crucial problem to work on, but it was pretty interesting in Seattle because for a couple of summers ago, you had 3 companies with multicolored bikes were littering the streets of Seattle. Right, there were yellow ones and green ones and red ones, and there was a company from China called OFO that was doing anti-competitive practices where they would offer free rides basically forever in order to try to drum everybody else out of business. And the yellow one had their own tricks, and there were stories of people picking up each other's, companies picking up each other's bikes and trucks and throwing them in the canal in order to try to fight it out. So it was really kind of a war for business in the streets of Seattle. Since then, the city of Seattle imposed a fee for an operating fee, and 2 of the companies backed out, and so now it's a little bit calmer now. But so we were partnering with the city of Seattle to take in all that data and feed out reports to the city of Seattle. And the reason why we had to do it as opposed to the city of Seattle was because the Freedom of Information Act requires the city to be able to have to release information on demand, right? And so we were able to set up kind of a legal trick where we're not required to do that. And the reason the city didn't want to do that is because as people may know who look at mobility data, but it's extremely sensitive, right? You can work out kind of everybody's comings and goings if you had access to this stuff. To this stuff. Even something as innocuous as bikes, you kind of know where they live and where they work and where they go and how often they work. And so we needed to, even when you try to anonymize things and take out names and social security numbers and everything, it still turns out to be able to you can show that it's pretty easy to work out a lot of information that you're not supposed to share. And so we were trusted to have that information, but the city of Seattle wanted reports on, well, who's using this service and is it equitable and are they following the rules and so forth, these kind of broad questions. And so we were able to try to answer those questions for them. But in the meantime, we were able to kind of look at the data and do some equity research, which is where we got some of these ideas from. Okay. So in this dockless bike, I should say it's bike share. In many, this is actually pretty common now, but a couple of years ago you had to kind of explain this. But there was, version 1 of bike share was, there's a station, a docked, you plant these stations over at various locations around the city, and you come and you park your bike there, and when you rent one, you put your money in or swipe your credit card, ride your bike somewhere else, and go find another station to drop it off on. The dockless approach, which again is ubiquitous now, so I don't know if everybody should be familiar with this, but you just leave it wherever it is, right? So you can, you find the nearest one with your app, and then you ride it wherever you're going, and just drop it off on the side of the road. This does require that the companies themselves have what they call rebalancing, which is they'll pick up some bikes in a truck and move them back uphill, right? Because people tend to ride downhill or toward the touristy areas and not away and things like this. Or if all of a sudden it rains in the middle of the day, then nobody wants to ride the bike home, and so you have to end up rebalancing things. Fine. So the idea of demand prediction was useful for the companies, of course, so they could rebalance appropriately. But it's also useful for the city to understand equity concerns, like where are all the rides actually being taken, right? We actually want to understand, have some indication of who's using this service and why. Okay, so this falls into this pattern of take a bunch of history and try to predict the next time step. And you have sort of spikes in time based on commuting hours, and nobody rides bikes at night. And so that's in time, in the time dimension. In the space dimension, you can divide everything up into a grid and just look at how many rides were taken in each grid, and that's a rough estimate of demand. I honestly shouldn't actually be saying demand, because it's kind of the same problem as crime. We don't actually know demand, right? We have a proxy for demand based on what rides are taken, but if no one has any bikes available in their neighborhood, then we don't know what the demand is, right? Maybe they had zero demand, or maybe they had a lot of demand and they just couldn't find one. And so I've been a little bit loose in this talk, and but we're aware of that issue. But this is the ride prediction conditioned on where the bikes are is really what this is. Okay. So the only thing I really want to show in this slide is that you can make these little, you can run all these different kinds of models that I outlined in the past few slides. A REMA is a time series prediction model, and Lstm is a deep learning sequential thing, and I mentioned Lstm and so on. And the point here is that 3D CNNs work better than everything else. And then this funny business with 3D CNN plus 1D plus 2D, this is the idea of adding in additional exogenous data sets to your model. So not only are you trying to predict bike share rides based on past bike share rides, you're trying to predict bike share rides based on past bike share rides, as well as weather, as well as topography, as well as bike lanes, right? Which obviously have some effect on, if it's raining, people don't want to ride. So when you incorporate weather into the model, it's able to train a little faster and take advantage of that and make better predictions. Similarly with, nobody likes to ride up hills. So if the model is aware of where the hills are, it can do a better job of predicting things. And so this shows that the error goes down. It's a little bit hard to interpret some of these error metrics, but just lower is better is all I really want you to take away from this particular slide. And then you can make these pictures, but what's difficult about interpreting some of these results is that these things all look like population maps, right? And so the predictions are all concentrated downtown, and so the actual error is harder to see in an aggregate view like this. But at least it looks roughly sensible. You can sort of tell here that it misses, in this particular version of the model, it was missing some of this yellow area down here, meaning that low demand areas or low ridership areas tend to get mistaken as just zero. And so there's some tricks you can try to do to fix that. So I guess one takeaway from this is that it's all very subtle, right? You in order to do a good job of a bike share demand model, there's a lot of things you need to think about. And we are one step back trying to think about how to help all possible models. So we don't necessarily have the best possible bike share demand model, nor do we have the best possible ride share demand model. That takes a significant research effort just in that domain. But what we can do is try to think about broadly how to support all these models. So key thing is 3D CNN, and we're not going to talk about particular methods anymore. And then the other thing is that adding in these extra data sets helps, right? That's an important thing to do if you want to have a more accurate model. Okay. All right. So then, what's this idea with EquiTensors? Well, the observation is that more data is available now than it's increasingly available, and in particular, there's these open data portals. Seattle has one, San Francisco has one. Every city has one nowadays. But some of the predictions about how this data would be used have not really come true. It's been a little bit difficult to, they're all out there. There's these portals, and honestly, the history of these things was kind of a preemptive strike against Freedom of Information Act requests. Was to say that it was going to cost too much money to try to respond to these requests on demand, and so the idea was, let's just dump out on the web as much as we can and let people self-serve, as opposed to us having to kind of scramble to respond to requests. And that, for that purpose, it worked pretty well. But there were some predictions made about, like, oh, well, this will start a whole new ecosystem of startups and research projects and so forth will use this data. And to some extent, that's been a little bit less than people hoped. And one of the reasons is in my core area of computer science, we aren't doing our job right? It's difficult to integrate data. It's difficult to use this stuff. It takes a lot of code. It takes a lot of expertise. And so you can kind of wave your hands and say, well, now that the data is available, you should be able to make cool predictions, in your models, but it's just not that simple. Okay, so our thought here, so that's observation one. There's a lot of data available, but it's kind of hard to use. Another observation is that in city context, everything's interconnected, right? Cities are complex systems where there's a lot of interdependencies. And I was struck by this in particular I went down and spent a day with, me and my students would spend a day with a place called SERPI, which is the Center for Reinventing Public Education. And they're kind of a charter school, think tank, and they do some research on education. And it was funny because most of the talks we heard that day were essentially about transportation, right? So you think, well, why are these education people? Well, I mean, I'll ask you all, why are the education people worried about transportation? That was a sudden, I guess I surprised people with the question. So everything's interconnected. Why is the education think tank mostly concerned with public transportation and other kinds of mobility questions?
Looks like Colin, you have an answer.
Hello.
Go ahead, Colin.
I guess those. Oh, yeah. I guess those. It seems particularly you mentioned that it's having to do with charter schools. I know that I've heard a lot of criticism with charter schools that they tend to be kind of spread out and not necessarily where the populations they want to serve are. They're often located away from the kind of most populations we're trying to serve. So trying to get people to those schools, I can see could be particularly, but for all schools, but for charter schools in particular, I can see that being very useful to kind of allow them to best to fulfill their mission the best way possible.
Yeah, I mean that's right. I mean the difference between one bus ride to one bus hop to two bus hops is night and day, right? If you're two bus hops away from the group from the population you're trying to serve, you fail. It's that simple. And so they were very concerned with like, okay, what can we do to try to influence? If we're going to put it here, what can we do to try to influence transportation, or how do we reason about that, or should we subsidize this with Uber rides or something? So they're thinking very creatively, and it's about access, and without access, there's no point even talking about the pedagogy at the school. So that struck me. But really, this is true in everything you look at, right? If you look at garbage routes or something, that depends on zoning laws and housing prices and history and so forth. So everything's interconnected in the city, and that suggests to us that there may be, could we learn some kind of underlying city features from the available data and let people use that in their prediction problems, as opposed to having to pick out exactly which data sets are going to be influential for their prediction problem? Can we just sort of give them a where everything's kind of baked in and you use this? This is a bit of an aspirational idea, but this is what we were motivated to do. And moreover, just as a practical concern, it opens up some possibilities, because you can imagine the same agencies that are paying for and standing up these open data portals to give you access to the raw materials of the data, could they also give you access to these cooked products? And if you're going to get in that business, you also now have an opportunity to adjust for biases and maybe control for privacy. And so maybe you could release data that you otherwise cannot release on the open data portal, because it's not really open data, it's sensitive data. But you might be able to release a set of learned features that incorporate some of that signal, right? It may not be, it's not quite so risky as releasing it raw. It can also democratize access, maybe, because it doesn't take so much engineering work to try to software engineering work to try to figure out how to incorporate 100 different data sets. You can just get access to this one thing and make use of that. You can also maybe kind of control the usage. You can kind of put legal encumbrances on it. Say, if you're going to use this data, here's what you need to understand about how it was collected. Here's the biases you need to understand. We don't allow you to use it for this. You have a little bit more control over how it's used if you have it all locked into one block. So there's a bunch of potential advantages that we're imagining if we succeeded this down the road. Okay, so how does this actually work in practice? Well, if you want to build a model that incorporates different kinds of data sets from different kinds of sources, and I made the argument a little while ago that you do want to do that to improve accuracy, it gets kind of complicated, right? So you have 1D features like temperature, 1D in the sense of it varies with time, but it's just, we assume that the entire city has the same temperature. That's not really true, but a mesoscale climate model is not going to have the resolution to give you kind of sub-city temperature precipitation measurements or something. 2D features don't change in time, so they're things like the slopes and the presence or absence of bike lanes. They change every 5 or 10 years or something, but not on a monthly, weekly scale. And then there's maybe 3D inputs that are more dynamic things that are happening. And so you kind of need a different part of your model to incorporate each one of these 3 categories, and you got to figure out some way to fuse them together. And then you add some of your convolutional layers and do some work on your actual deep learning network design, and then finally make a prediction. But this, the engineering involved in this, and honestly, the computation, the training time involved in this gets pretty complicated. And moreover, you don't necessarily even have access to all the data sets, as I said before. Some of these could be sensitive, where you're not allowed to get direct access to them. Okay. And so our thought here is to say, well, what if we can take all these different data sets, learn some shared representation of them, by this yellow block, and then downstream, for the people who are interested in bike share demand, can just use this shared representation, connect it to their bike, to their own data, their bike share demand history, then train a model and make a prediction, and hopefully do better than just bike share demand alone, but without all the engineering and difficulty of trying to incorporate all the different data sets that may have an influence, that may influence the accuracy of the bike share demand. Okay. So I won't pause for a question there, but I will say that if that doesn't make sense, please jump in and ask a question, and I can stop and say more about what we're up to there. But that's the basic idea. And I'll point out that this is not a wild idea out of the blue. This is actually kind of common practice in other areas. So, natural language processing apps nowadays, they're, to a first approximation, nobody trains their own model, right? Because you don't have access to all the text in the world, but Google essentially does, right? And so the model that they train on all written text, you want to use that as a starting point and then customize it for your particular application, right? And so these pre-trained word vectors, as they say, in models like BERT and GLOVE and earlier Word2Vec, have very impressive properties and are a better starting point for your NLP machine learning application than trying to train it all on your own company's set of written documents or something. And same thing with images, right? You start with ResNet 50 perhaps, or ResNet 18. There's different models out there, but they all start from ImageNet, which is a huge data set of natural images that have been taken in front of the world. And so you don't have access to the computational power typically to do as good of a job as they can, but you do have access to their pre-trained models. And so we're really just trying to take the same idea, except in our case, it's less about the scale of the data and more about the complexity and heterogeneity of the city data. But the same kind of idea is can we give you a starting point to get access to the city data without having to do everything yourself? Okay. And so that's this project. We used to call it EquiTensors, and then when we added fairness, we called it EquiTensors, because really we kind of realized that the main point of this is to adjust for fairness, that I'll talk about in a second. All right, and so it looks roughly like this. You have this encoder decoder. There's better, fancier network models to use, and we're exploring some of those. But the simplest idea would be taking a bunch of data, encode it into some what I'll call latent representation, and then try to reconstruct the input from this latent representation. And to the extent that you can do a good job of that, that means your latent representation is good and has captured all the information. And the training process produces this. Okay, and so the loss function looks something like this if you care about that kind of thing. This is there's fancier ways of doing this as well, but the simplest loss function might just be L1 norm. All right, and so what does this purple thing look like? You actually have a lot of flexibility in what this looks like. It could be kind of any block of numbers. The idea is, how many ever numbers you think are important to capture the full complexity of all the input data, you could try it out. We happen to choose something where we wanted to keep the spatial dimensions the same as the original, as the original grid of the input data for interpretability reasons. So we want to be able to take a slice of this thing and look at it on the map and try to understand that we see the city of Seattle or we see the city of Chicago in the way the data is done. That's not required though. You can sort of do whatever you want. And so we end up with a time series here. And really all that's happened here is we've taken 25 or so data sets that are raw and kind of compressed them down into 5. So you can think about each one of these little grid cells has 5 numbers associated with it. And we may or may not know what those 5 numbers mean, but the hope is that with those 5 numbers, you are capturing the dynamics from 25 original input data sets. Okay. All right, so how this thing is used again, downstream, you've got a bike share task that's X by Y by T by just one feature, bike share, and you've got your EquiTensor thing that you downloaded from the website or something, and you concatenate those together, and then you go set up your problem. And so now you have 6 features to play with as opposed to just one, and hopefully your model does a better job. All right. So that's the basic idea of integrating the data, but there's a problem with this with respect to equity. And the problem is ubiquitous. Everybody has this problem, but we've potentially made it, with what I've described so far, we've potentially made it worse. Okay. And given the seminar series, I don't need to motivate this too much, but all these mobility questions have significant equity questions you can ask, and a lot of the answers are not great. So with rideshare, you've got plenty of papers out there that are showing that Uber seems to offer better service in areas with more white people. That's not great, and there's many different reasons for that. And I'm going to talk about one particular one that underlies everything. And same thing with bike share. One of the concerns, and when we talked to the city of Seattle early on about this stuff, was they wanted to know who was using it, and they were concerned about subsidizing a bike share system that was in support of the mammals. And so what's a mammal? A mammal is a middle-aged man in Lycra. And so the idea here was, if these are the wealthy bike owners who commute every day to work anyway on their own bike that they own, if we're basically providing an entire bike share service that's basically just helping them, it's not worth it. Like that's not the why we did this. We did this for health reasons and for mobility reasons for other groups, but we have to actually monitor that to be able to see what's going on. Okay. And then in some cases, it may actually worsen travel disparities for the poor. So I want to step away from transportation for a second and just remind people who have thought about this, or maybe show you for the first time, why these, my claim is that every one of these data sets you're going to use is horribly biased. And I won't say irreparably because we actually try to repair it, but you're not going to be able to get away with using this raw. So this is from a Bloomberg article several years now, I guess now it's about 5 years ago, on the Amazon Prime Now delivery area. Okay, so Amazon Prime Now is this service that it's still out there in some form, but it would give you like a 1-hour delivery time, right? So they're trying to locate their warehouses and their delivery supply chain closer to the local areas. And so the folks at the computational journalists at Bloomberg, drew these maps about who had access to the area. And so this is a map of the city of Atlanta where I grew up. And, the gray area is everybody that got access to the service. Well, everybody in the north half of Atlanta got access to the service, and nobody on the south half of Atlanta got access to the service. What else is true about the north half of Atlanta versus the south half of Atlanta is that the north half of Atlanta is predominantly white and the south half is predominantly black. It gets worse. In Chicago, everybody got access to the service except for the south side. In Boston, it carved out a donut shape around Roxbury, which is a historically black neighborhood, right? And so this is crazy, right? So the thought here is you can ask the question, well, how did this happen? Did Amazon engineers, do their dastardly mustaches and intend for their model to be racist? Well, no, right? They just, in fact, the title of the article was, Amazon doesn't consider race in its models, but should it, or something. And the idea here is that, what did you train this? So they trained a little model, right? They looked at buying history and they looked at all this information to try to figure out where they should offer this. But those inputs, right? Buying history reflects, 100 years of systemic racism, beginning perhaps, well, not beginning, but perhaps most insidiously, sanctioned by government sanctioned in the 30s with redlining, right? And so back to Atlanta, they would release maps that tell developers don't invest in these areas because they're considered hazardous. And they were not even barely pretending to not be racist about that, right? Those were the black neighborhoods they were saying don't invest in. Okay, and so if you put down maps of redlining back in the 30s and you look at like housing prices today, you see the same patterns, right? This is now 100 years later. So any data set you see, buying history, income, anything that's got a spatial extent around the city is going to reflect these policies from 100 years ago. Okay, so I'm not a sociologist. This wasn't really my, I don't know anything about this. It wasn't really my problem. I don't really study racism and so on. But when you start suggesting that we're going to automate it, it becomes my problem as a computer scientist, right? Because I'm now entrenching these ideas into an automated system that's going to make decisions about bike share demand or anything else, right? And so we have to take on the responsibility as people who are helping to automate things what automation means is there's no human attention on it anymore, or less human attention on it anymore. And so if you're going to take humans, reduce their influence on the decisions being made, that means somebody has to pick up that responsibility that used to be, they used to be accountable for because they're making decisions. Now it's us, right? Now it's the technologists. And that fact was overlooked for the last 10 years and is now in the last couple of years, tech companies are starting to realize this. But in the spatial context, this is the number one thing in my mind of what's going on, is that anything that has a spatial extent, you're going to be sensitive to what's going on in different neighborhoods. But just one other example that I like to mention: Mark Hallenbach is a transportation guy at UW and runs a long-term center called TRACK. He's fantastic. He goes on TV and talks intelligently about what's going on in the city of Seattle. So he's a lot of fun to talk to. He's an encyclopedia. But one of his examples was just, with the rise of data science, it was really exciting to say, oh, we've got these really rich data sets now. We've got a card swipe system for public transportation, which every city does nowadays, and ours is called ORCA, one ride, one regional card for all, I think is the acronym or something. But you get on the bus and you swipe your card, and you pay, but you also track who you are and where you're going, which is a very rich data set to be able to do transportation engineering with. It's fantastic. But who has these cards? Right, you can also pay with change, right? You can still get on the bus and throw in your change the same way you always could. So who tends to have cards? Maybe I'll pause again for that one. Oh, well, I guess I said on the bottom of the slide, maybe it's not that much of a clever trick, but I've got a card, right? I work at the University of Washington, right? Colleagues at Microsoft have cards, colleagues at Amazon have cards here in Seattle, right? So this whole, the entire data set skews toward wealth, right? And so if you base your transportation engineering design on this really rich, interesting data set, you're going to design a system for the rich people, which is precisely what you don't want to do. The entire reason why the public transportation system exists is to manage equitable access to the resources of the city, right? Not to, if you wanted a system that built for rich people, you wouldn't even need the city government to do it. You could just let the market figure it out, and you have that. Okay, so Mark Hallenbach is too smart for this, and they're all over this. The other way of measuring ridership is to, there's a pressure plate on 30% of the buses, and you step on the bus and you get a click and you know that someone got on. You don't have any of this really rich, interesting metadata about who they are, but at least it's ridership. And so you can make once you can look at the regions of the city. So finally, back to this map, what this map is showing is where do these two measures disagree, right? And so it turns out that yes, in poorer lower income neighborhoods, that's where they disagree the most. And once you know that, you can make some adjustments and fix that. And Mark was all over that. But in a lot of these areas, you throw your data over the wall to some consulting firm that does data science work, or to some set of students in computer science like me. We're going to screw it up, right? Because we don't understand the context of some of the biases there. We're going to give you a prediction based on biased data. Okay, fine. So my view is that raw data is not what you want, right? You never want the raw data, right? We know that the raw data is biased. And oftentimes we know how it's biased. And so we want to adjust this in some way. And so EquiTensors, we have one way of adjusting this, but there's other ways as well. We've had some other papers where we try to look at ways to do this. And there's just some quotes here that I've picked up over the time when I've mentioned this, but just recently I'll let the data speak for itself when it can clean itself. Which I thought was kind of fun. And clean data is like clean money; it doesn't exist. Okay, so you can take those if you like them, you can use them, and if you don't, then sorry. But the reason I try to hit this so hard is that it's antithetical a little bit to the culture of science engineering to accept anything other than raw data, right? Of course I need raw data, right? My science depends crucially on getting the exact correct numbers, but we know that those exact correct numbers are biased in these terrible ways, and so I claim that you're not getting the answer you think you're getting when you try to build a model or design a system based on that. Okay. All right, so maybe I'll skip this, but there's different, if you want to be interested in fair machine learning, there's been a ton of work in the last few years. It's really kind of exploded, and there's different ways you can attack this. You can try to adjust the raw data, you can adjust the algorithm, you can train up your stuff and then adjust it after the fact. And we're trying to do more on the pre-processing side, so adjust the data before other people use it. Slide's a little bit dense. The only thing I want to point out here is that given a whole bunch of work in fair machine learning, spatial and spatiotemporal extent of fairness is less studied, and so we have a couple of metrics to reason about fairness that had to do with if the population in this grid cell region is a certain proportion African American, and the demand prediction is lower than it should be in that area, then something is unfair. You need to have this kind of balanced out based on race or income class or education level or what. And so we have a proposal for how to work that out. We had a couple of papers where we talked about that, fairness in spatiotemporal context. And the takeaway that I was really exciting about that, I think, is that you can adjust for fairness kind of for free in some cases. And what I mean by for free is that you imagine that, well, if we're going to try to make it more fair, somehow we're going to get less accurate, right? Because we're not using the real data, we're using sort of adjusted data in some sense. And it turned out that wasn't really the case. That wasn't always the case. And the reason is that the model tries to cheat, right? When you do this training process, it tries to cheat and say, oh, well, I figured out what you're doing here. It turns out that you never should send any bytes to the poor neighborhoods, right? Because that would give you the highest possible, the highest possible accuracy. But that's not actually the right rule, right? that doesn't actually give you the best income if you're a bike share company, right? It's just that's kind of a shortcut because of the biased data. And so when you force it to be fair, at least in some cases, it becomes a regularizer, which is a way of it forces the model to find a more general solution than your shortcut cheat sheet of just discriminating against poor people. So in some sense, there's kind of a free lunch there. By making it more fair, you also improve accuracy. But we don't. I confess we don't totally understand exactly when that happens and when that doesn't. We're just trying to understand that. Okay, so that's one trick. I'm going to wrap up here in a second. The way we do fairness now with EquiTensors. We had this encoder decoder a few slides ago. The new thing we add, which is not really our idea, but we've adapted it for our context, is to add a little adversarial model. And so what this thing does is say, given an equitensor, I'm going to try to predict race. I'm going to try to guess what the racial breakdown of every grid cell is. And to the extent that I'm able to do that, that means that equitensor is unfair. Okay, and so penalize the overall model by how well it's able to guess race is a way to adjust for fairness, and that works pretty well. So I'll quickly just summarize this. You do want to incorporate exogenous data. Just giving up on this whole idea altogether and just sticking with your old data isn't good because your accuracy suffers a lot. Using these equitensors is almost as good as being perfect about choosing exactly the right data sets you want and building a custom model that only uses those. We do almost as well as that. And then it outperforms all the simpler things that don't use a lot of deep learning or don't use anything fancy. And then with fairness, we can't claim that it scrubs your downstream application and makes it fair, right? There's no way to control that, right? Because that's your data, right? Your data may be biased, and we don't control how you use your data. But what we can sort of guarantee, well, empirically, not really guarantee, we don't have a proof of this. But what we do seem to encourage is we don't make it worse, right? So by incorporating all these extra data sets in that have their own biases, we're able to not exacerbate fairness issues by incorporating this, which is important because these discriminatory signals that I mentioned are totally pervasive, right? They're in every data set you may use, and so we try to do no harm and make things not worse. And then moreover, as I mentioned, the accuracy degradation is not too bad, which is pretty nice. Fine. So exogenous features matter. Throwing in the kitchen sink and all available data sets is pretty good, and then incorporating fairness doesn't throw you off a cliff in terms of accuracy. So it seems to be working pretty well. And this is my last slide, I guess. So the data is becoming more and more available, but it's still very difficult to use. All of it's very polluted with bias and fairness issues. And so we want to try to make it easier to use this stuff, but you absolutely must. It's not optional to try to adjust for discrimination in some form, because otherwise you're just going to propagate these historical discriminatory signals from 100 years ago. And then it looks like it works pretty well so far, but there's a million things to try to work out here. Variants of the model, parameter tuning this, different kinds of network designs, One thing I'm really excited about is trying to figure out how you can train a model in Seattle, but then deploy it in like Austin and have that make sense. Right now, that wouldn't work with the way we do it currently, but we have some ideas on how to maybe make it more transferable. So anyway, so if you're interested in any of this stuff, happy to chat about where to go from here. And then the code, I should have put it on here, but the code is available on the project page that I think I provided to folks. So you can take a look at that and play with it if you want. I think I ran a little long, so sorry about that, or quite a bit long. I apologize. I got excited. I'll stop there and let people see if they have any reactions to any of this.
Yeah, thank you so much. That was very interesting. That was terrific. I encourage everyone to go ahead and use the Q&A button on the bottom of your Zoom screen to ask questions. And we have one already from Sumin Wu. I love this work. Could you please share the links to the code and project website? Sumin, we will share those. I think that chat function doesn't work for you if we do send a chat. So what we're going to do is maybe go ahead and send that over email to all the registrants so that you can have access to them. Other questions, please go ahead and type them in the Q&A. In the meantime, Bill, I wanted to make a quick reflection and ask a question. This reminds me of social scientist that worked on research design, and his recommendation to doctoral students was know your rats, suggesting that you have to know your data.
Mm-hmm.
And that's really fundamental to whatever you want to do with it. And this is kind of a huge warning, your presentation, and an opportunity for those of us that really work on city data. One question about assessing fairness, assessing really disparities in distributions that are related to people, to race, ethnicity, income, the characteristics that you were examining. They often require a reference group. I saw you use the region, for example, and I'm wondering what other reference groups sort of spatially you've used, zip code, the city, and then what are the pitfalls of doing so?
You know, as I mentioned, this is really sort of an experimental, you know, could this even conceivably work kind of approach where we are right now. One area of many that I'm not happy with where we are yet is, you know, cutting up all this data into a regular grid and going from there doesn't really make a lot of sense, right? So trying to figure out how to, you know, some data is provided on census tracts, other data is provided on zip code, other data is provided more individual, you know, we actually have, you know, GPS traces or something like that, and being able to actually incorporate all that data in full fidelity seems important. That's not quite what you asked though. So I guess I would say what I'm hoping to do down the road is not have to select one particular reference model and regrid everything to that, but rather factor that in more carefully. You know, if we're going to lose fidelity, that's maybe okay. I mean, it's kind of required by this approach, but do so with some intentionality. Right now, we're just throwing away all kinds of information because we force everything to be on the same grid, and that doesn't make a lot of sense. I think maybe you were asking about something slightly different though, which is if you're going to reason about, I don't know, population distribution, you know, along race or income or anything else, what do you compare it to? Is that?
Yeah. So how do you assess whether your distribution is off? If you have an overrepresentation of X group or an underrepresentation of X group.
Well, so here's what's tricky, and I have a couple of slides on this. I didn't include in this talk, and I maybe wish I had. It's really tricky because let me say this: every machine learning paper has an assumption about representativeness, and what they mean is that if the training data doesn't represent the population, then all bets are off, right? But in the real world, you don't have the population, and the reason is that what we want is not the population in the world we have, but we want the population in the world we wish we had, right? Like there is no ground truth is a problem, right? The ground truth is in a parallel universe where we didn't have 100 years of systemic racism, and we don't have that ground truth. And so in some sense, we don't, I think what you're getting at is we don't really know the answer to your question, right? We don't really know what is the, you know, with the counterfactual of if we had not had this you know, this historic racism, what would be the distribution of the city in terms of race or income or anything else. We simply don't know the answer. But what we do know from our sociologist friends, they know quite a bit about how some of the current numbers are wrong. Does that make sense? Like, we don't really know what the ground truth is, but we do know how things are wrong. And in my mind, it's irresponsible to not incorporate the best we do know about these things. So, for example, like the little argument I made about, redlining still shows up in housing prices. To not make some attempt at adjusting housing prices based on that is what seems irresponsible. But you're pointing out that we can't know for sure whether it's in some sense correct or not. There's no real way to gauge that, because it would require the counterfactual for the entire history of the world.
Thanks, Bill. Let me follow up with another question from Scott Mora that is related. It's great talk. It seems that the identified racial inequities in model predictions are known unknowns. But what about the unknown unknowns? That is, what if racial injustices underlying your measurements, but it's not actually understood overtly and obviously?
It's really fantastic. So I'm hitting on, honestly, some pretty narrow manifestation of inequity, right? It's all over the place, right? And you mentioned how the data was measured. Absolutely. I mean, we saw it with COVID. We've seen this terrible examples of this, right? Where we simply weren't measuring, Black and brown communities as well as you were in other areas, and so it looked like it wasn't as bad as it was until 5 months later. So every step along the way has these biases in there. And so I think let me leap outside your question a little bit. I think one conclusion one might draw from this problem, you think, oh my God, this is impossible. Every step is filled with biases. We're screwed here. One argument people might make is that's why we should be very conservative about how we apply technology. And they're right. I tend to agree with that. But I'm personally, as a technologist, I guess, I'm not quite comfortable with the idea of letting the public sector fall so far behind what private companies can do, right? So I'm nervous about throwing up our hands too much and saying, well, because all these sources of bias are there, we want to be very slow about how we deploy technology. What I'm worried about is that means that human services will still be paper and pencil while everything else is completely automated. And so I really want to try to figure out what we can do about it as we can. So it's a bit of a dodge of your question. You're absolutely right. There's sources everywhere. And our broader NSF project is around this notion of data equity systems. Mm-hmm. And we're basically trying to go after that to say, how do you rethink the design of systems from the ground up to bring in equity at every possible step? And so this EquiTensors project is really kind of one slice of that. But to try to bring that in as a first class design requirement at every step is really what we're after. But you can probably tell by the way I'm answering the question, we don't totally know how to do that yet. This is just we're starting to think about it. But you're absolutely right. It's a great observation that this is the entire data pipeline is polluted with possible biases, unknown unknowns.
Bill, we're gonna take two more questions. So I'm gonna mention one, and there's room for another one if anyone wants to ask it. This comes from Sumin Wu. Say an organization like Uber has a fairer data representation. So some representation that is more fair or more accurate in terms of fairness than what we observe. What is your opinion on whether that organization will actually should reflect that in their product system or design?
Yeah, I hope I didn't come across as that. I don't trust Uber. Nobody should or nobody does really at all. So I think where I would see this going is that if there are methods that can mitigate some of these harms, you end up having to pass laws that you start to get some visibility on what kind of laws you might want to design to require this. And I don't think we know the answer to that yet. I'm not sure. It may be hard forever, but to explore what I think you have to invoke the legal process at some point. You're not going to, we can't really leave it up to companies to do this on their own. There has been some good news lately where, horrible failings in this area start to bite the companies in terms of PR, right? There's starting to be a little bit more recognition of this. But I personally wouldn't trust that mechanism alone to try to make sure that people are doing this. If they can squeeze out a few more % of accuracy by being unfair, I don't see them sacrificing that just on their own regard. So I think the idea of the research would be to try to clarify what should the nature of the laws be that say you must, for example, there's a lot of work on auditing and monitoring and say, you must achieve this fairness metric or something under these contexts or something. We don't know how to write that write those rules down now, but maybe that's where we're going to be in the future. And then Uber would have to show as part of the reporting that if you're going to operate in a city, you have to show that you're achieving some sort of equity goal that's quantifiable, and we're just not quite there yet.
Not unlike what happens with the bike share, some of the bike share contracts now, that certain amount of supply needs to be offered in certain areas.
Yeah, exactly. And I think with Uber, there are some people in the room may know better than me, but there have been some progress on these kinds of things. But it's not been quite as mathematical as what we're kind of advocating for.
Okay, good. Any other questions from the audience? Okay. Well, Bill, I want to thank you very much for your time. This has been a wonderful seminar. Great start, by the way. I failed to mention that this was our first of 4 seminar series. So thank you very much for leaping us forward. It's been wonderful to have you here. It was a great context, a great way to go ahead and launch the seminar series. So thank you. We have our sponsors again. CITRIS and the Banatao Institute, Berkeley Engineering, and of course, this is primarily put together by the Institute for Transportation Studies. For the next seminar, we have March 5th, giving us a slightly different perspective. So not the academic perspective that Bill provided right now, but the urban diverse city perspective with Ramses Madou, who is division manager for the planning, policy, and sustainability in the Department of Transportation for the city of San Jose. And we have March 19, also a startup perspective with Liz Adams and Doug Alley from Paravision. So we look forward to those presentations. Again, Bill, thank you very much. I'm sure you'll hear a virtual applause from everyone in the audience. For those of you who joined, thank you for being here. I hope you enjoyed the talk. Until the next time.